Hello, everyone. Today, I will be presenting our paper, Equivariant Spatio-Temporal Self-Supervision for LiDAR Object Detection. Self-supervision enables the learning of generic visual representations of unlabeled data by completing tasks designed based on human intuition about what information can be inferred from its inherent properties without the need for explicit supervision. The availability of large amounts of unlabeled LiDAR data thus makes self-supervised learning a natural choice for improving the performance of perception tasks in limited label scenarios. In this work, we study the role of enforcing invariance versus equivariance in self-supervised learning on LiDAR point clouds. Invariance of the function f to a group of transformations g means that the output representation does not change with the applied input transformation, whereas equivariance of f to g means the output representation changes by some applied input transformation. We are interested in better understanding the effect of and improving methods for equivariant pre-training for LiDAR point clouds for object detection, since it inherently has an equivariant component. For example, bounding box regression should be equivariant to geometric transformations applied at the input. Existing works, such as STRL, either learn spatio-temporal invariance or train only for spatial equivariance, as in point contrast. We propose the framework ESSL 3D. We consider LiDAR scenes applied with a series of spatial and temporal augmentations to train a 3D feature encoder under a joint equivariant contrastive learning objective and a flow equivariance objective. To encourage spatial equivariance, transformed view of a scene are contrasted at the point level as well as passed to a classification head to predict the applied geometric transformation. To encourage temporal equivariance, the network is trained to minimize the distance between sequential pairs of LiDAR frames in the voxel feature space, where the feature map of the first frame is warped to the second frame. Our goal is to train a network to be equivariant to certain spatial and temporal transformations in order to learn meaningful geometric representations that aid the network in performing dense scene prediction tasks. Consider an input point cloud from a sequence of LiDAR scenes. First, we focus on common global rigid geometric transformations that are invertible: rotation, translation, scaling, and flip. We train the network to be equivariant to a group of spatial transformations in two ways: through a contrastive training objective and through an augmentation prediction objective. The network is trained to retain the information of the transformation that was applied at the input. That is, the features are equivariant to the input transformation. In addition to spatial augmentations, we exploit real frames that are captured sequentially to prove additional self-supervision. The key insight for temporal self-supervision is that the features of the network should evolve in a manner equivariant to how points move in the real world. We term this 3D scene flow equivariance, where the 3D scene flow is a vector field that describes the motion of points in a point cloud frame at some time instance to locations in a different time instance. Final loss function used to train the network is the sum of the contrastive loss, the classification loss, and the L2 distance loss, all of which are brought to similar scales through loss coefficients. We use the Kitty 360 and the Waymo Open Dataset for pre-training and perform fine-tuning for the downstream task of 3D object detection. These are the results of 3D object detection with voxel RCNN pre-trained on Kitty 360 and fine-tuned on Kitty under different data splits. We compare the performance with the recent state-of-the-art self-supervised learning methods for LiDAR scenes by initializing object detectors with each pre-trained model. These detectors share a common sparse convolutional 3D feature extractor backbone and initialized with the same model pre-trained on Kitty 360. We compare these fine-tuning results against point contrast, STRL, and also, as well as fine-tuning from random weight initialization denoted as no pre-training. We observe the best or second best performance in general and specifically outperform point contrast in STRL and perform on par with also. We conduct an ablation study on the spatial and temporal equivariance constraints and evaluate on the task of training voxel RCNN on 5% of the Kitty data. We report the 3D mean average precision for all three object categories with 40 recall positions. This study shows that enforcing both spatial and temporal equivariance constraints performs the best overall, and both equivariance constraints contribute.